Welcome back to our deep dive into number theory. Last time we explored prime factorization. And today we're moving on to a concept that's foundational to statistics, but still relevant to our number theory journey, the z-score. You've probably encountered z-scores before. But today we're going beyond the basic definition. We're going to uncover how z-scores help us understand where a single data point stands in relation to a whole set of data.
It's a bit like finding a specific grain of sand on a beach. But instead of sifting through each grain, we have a powerful tool that tells us precisely where that grain is relative to all the others.
Okay, I like that analogy. So to make sure we're all on the same page, how would you define a z-score for someone who might be encountering this concept for the first time?
At its simplest, a z-score tells us how many standard deviations away a data point is from the average, or mean, of the entire set of data.
So to really grasp z-scores, you first need to have a solid understanding of standard deviation. Can you give us a quick refresher on that?
Standard deviation is essentially a measure of how spread out the data is. Imagine you have a group of numbers. If those numbers are all clustered close together, the standard deviation will be small. But if the numbers are scattered far apart, the standard deviation will be larger.
So a small standard deviation means the data is like a tightly packed flock of birds, while a large standard deviation is more like birds scattered across the entire sky. I'm starting to see how this relates to the z-score.
Exactly. And the z-score tells us where a specific bird is within that flock, or within the entire sky, relative to the average position of all the birds. If a bird is flying above the average position, it'll have a positive z-score. If it's below the average, the z-score will be negative.
That's a great way to visualize it.
Mhm.
Now let's get down to the nitty-gritty. How do we actually calculate a z-score? There must be a formula for this.
There is. The formula is z, where x represents the individual data point. E is the mean of the entire population, and sigma is the standard deviation of the population.
So we're taking the difference between the individual data point and the mean, and then dividing that by the standard deviation. What's the intuition behind this division? Why is it important to standardize by the standard deviation?
That's a great question. Dividing by the standard deviation is what allows us to compare apples to oranges, so to speak. We might have data sets with vastly different scales, units, or spreads. By standardizing everything to the same unit, the standard deviation, we can compare them directly.
That makes sense. It's like converting different currencies into a common unit so we can see how they compare in value. But what if we don't have data for the entire population? What if all we have is a sample?
That's a common scenario in real-world data analysis. When we're working with a sample, we use slightly modified formulas that rely on the sample mean and sample standard deviation to estimate the z-score. This gives us what's called a t-statistic, which is very similar to the z-score, but accounts for the fact that we're dealing with a sample rather than the whole population.
So, the t-statistic is like the z-score's cousin, similar in concept, but adjusted for the uncertainty that comes with using a sample. This is all starting to come together so far. We've defined z-scores and looked at how to calculate them. But I'm curious, where does all this fit into the bigger picture of data analysis?
That's where things get really interesting. Z-scores aren't just about calculations. They're a gateway to understanding a data point's position within the overall distribution. They're directly related to percentiles, which tell us what percentage of other data points fall below a particular value.
For example, if my z-score for a test is 1, does that mean I'm in the 84th percentile?
That's a good guess. And you're close. It's actually slightly more nuanced than that. To accurately determine the percentile, we'd need to look at the area under the normal distribution curve that corresponds to a z-score of 1. There are statistical tables and software that help us do this.
Okay, so a z-score is more than just a number. It's a key that unlocks a deeper understanding of where a data point fits within the bigger picture. This is starting to feel a bit like detective work.
I like that analogy. And we've only just scratched the surface. In the next part of our deep dive, we'll explore how z-scores are used in more advanced statistical techniques and how they can help us uncover hidden patterns and insights in complex data sets.
I'm ready to dive deeper. Lead the way.
Welcome back to our deep dive into the world of z-scores. Before we move on, I want to pick up on your detective work analogy. It's a good one, because z-scores are often used in anomaly detection, which has a lot in common with detective work.
Okay, I'm intrigued. How do z-scores help us spot those unusual suspects in the world of data?
Imagine you're monitoring a network's activity for a large organization. You have a constant stream of data points representing the number of users, the amount of data being transferred, and so on, most of the time. This activity fluctuates within a predictable range. But what if there's a sudden spike or a significant drop?
That could be a sign that something's not right, like a cyber attack in progress. But how do we tell the difference between normal fluctuations and a real anomaly?
That's where z-scores come in. We can calculate a z-score for each data point representing network activity. If a z-score is exceptionally high or low, meaning it's far away from the average, it raises a red flag. It's like having a security guard for your data, constantly on the lookout for suspicious behavior.
So, in essence, z-scores are helping us establish a baseline of what's normal, and then alerting us when something deviates significantly from that baseline. That's a brilliant application. I'm starting to see how versatile this concept is. It's not just about understanding individual data points, it's also a tool for monitoring processes and systems over time.
Exactly. And that brings us to another fascinating application, process control. Let's say you're running a factory that produces thousands of light bulbs each day. Each bulb has an expected lifespan, but there will naturally be some variation.
Right. Some bulbs might last a bit longer, some a bit shorter, but overall they should fall within an acceptable range.
Precisely. And to ensure quality control. Manufacturers use z-scores to monitor the production process in real time for each light bulb produced. They measure its lifespan and calculate a z-score based on the average lifespan and standard deviation for all the bulbs.
So if a bulb burns out way too soon or lasts much longer than expected, its z-score would be pretty extreme, right? It would be like that bulb screaming, hey, something's off here.
That's a great way to put it. And by setting control limits based on z-scores, manufacturers can identify deviations from the norm and intervene before a small problem turns into a major one. It's like having a built-in alarm system for quality control.
This is all incredibly insightful. We've seen how z-scores help us understand individual data points, monitor systems for anomalies, and ensure quality control in manufacturing. But I have a feeling there's even more to uncover.
You're absolutely right. We haven't even touched on how z-scores are used in research to compare data sets measured on different scales, or how they help us understand the relative importance of different variables in a statistical model. There's a whole world of applications waiting to be explored.
I'm ready to dive deeper. Lead the way. Welcome back. It's amazing how z-scores can be used in so many different ways. We've talked about using them for anomaly detection and process control. And I know there are many other applications out there. What about using z-scores for comparing things that are measured differently?
You're right. That's another key use of z-scores. Think about standardized tests, for instance. The SAT and the ACT are both designed to assess college readiness, but they're scored on completely different scales.
It would be like trying to compare apples and oranges, right? How can we possibly determine which score is better?
Exactly. But by converting these scores to z-scores, we can put them on a level playing field. A z-score allows us to see how well a student performed relative to the average student who took the same test.
So, even though the raw scores are different, the z-scores would tell us which student performed better compared to their peers on each respective test.
Precisely. And this principle applies to all sorts of data. Imagine you're a researcher studying the factors that contribute to plant growth. You might measure things like the amount of sunlight, the amount of water, and the amount of fertilizer.
But those are all measured in different units. Hours of sunlight, liters of water, grams of fertilizer. How can we compare those to see which factor has the biggest impact on plant growth?
Again, z-scores come to the rescue. By converting each variable to a z-score, we can see the relative impact of each factor on plant growth. A larger z-score would indicate a stronger influence.
That's incredible. It's like we have a secret decoder ring for the world of data. We can take all these disparate pieces of information and transform them into a common language. That allows us to see patterns and make meaningful comparisons.
I couldn't have said it better myself. And this is just a glimpse into the power of z-scores. As you continue your exploration of data analysis, you'll find that this seemingly simple concept has applications in a wide range of fields, from finance and healthcare to marketing and social sciences.
This has been a truly eye-opening journey. We've gone from the basic definition of a z-score to seeing how it's used in real-world applications, to monitor processes, detect anomalies, and even unlock insights from complex research studies. What a powerful tool.
It's been a pleasure sharing my insights with you. Remember, the next time you encounter data that seems difficult to compare or interpret, think about the power of z-scores. They just might hold the key to unlocking the hidden patterns and insights within the numbers.
Thank you so much for joining us on this deep dive into the world of z-scores. We hope you've enjoyed the journey and gained a new appreciation for the versatility of this foundational statistical concept. Until next time, keep exploring, keep questioning, and keep diving deep into the fascinating world of number theory.